Hello everyone, this is the libhal biweekly meeting. It is August 20th, and I'm your host, Cleo Stell. So for our agenda for today, we're going to go over deprecating some packages. We talked about last week, or last biweekly meeting, about the new hierarchy and how the new organization for libhal and kind of what libhal looks like fully realized. And in that, we are having a bunch of repos that are being subsumed into other repos, so we want to talk about that. We're also going to talk about the shifting libhal-soft responsibilities. With the new packages that have been created, some of the libraries within libhal-soft no longer made sense to still be there, so they'll be moved to the appropriate other repo. I believe I'm keeping them there and just deprecating them in this, yeah. And then also we'll take a look at STM32 generic SPI because I think it's a really interesting, it's another pattern that I've always wanted to write up. I just haven't had the chance to, and now we finally have an opportunity to do so. So first off, let's talk about deprecating packages. So here's a partial list of the deprecated packages. I know there's a few more in here that aren't listed here, but we're deprecating libhal LPC40, STM32F1, F4, RMD, MPU, SPA, all of the ones over here. Now, deprecation doesn't mean that they're gone. We actually just took all that code that was there and we migrated it into the new repos. The reason why we did this is, I'm just going to repeat this. The reason why we kind of turned it into this smaller group of repos is to go from an open set of repos that can exist to a closed set of repos that can exist. We'll still add in new platforms as things go up, and now still be an open list, new platforms. But now that we've consolidated anything within the range of the same CPU architecture as being one whole platform, and just being an implementation of that platform, all goes into its own repo. But there's only so many of those things that exist out there. So really that list will grow very slowly. Whereas the list of storage, actuator, IoT, input, sensor, and that kind of stuff, those shouldn't grow much. There might be new categories that come out, but I think for the most part, we'll just have those categories. So now we will have, if anything, a very slow growth of repos. And then the only other repos that would grow into the libhal organization would be things that are like projects that implement something, like can opener, as an example. So things like TMP, which is a temperature sensor, that goes into sensor. ESP32 will end up in IoT. It's not there yet. PCA will go into expanders. That's its own little software area. Things that convert one thing to, things that give you can use one protocol to get more things out of that thing. Yeah. And then RMD, which is the RMD class of smart CAN-enabled motors. That will go into libhal actuator. And then one thing from libhal-soft that actually we'll talk about a little bit, or we're not going to talk about it later on, but one of the things that happened with libhal-soft is that with a couple of the things that were there, like RC servo, that should be inside of libhal actuator. And the other thing that's in there is, it didn't actually get there in there yet, but the SD card. The SD card driver would actually go into libhal sensor. So, I'm sorry, not sensor. Libhal storage. I don't know why. It starts with an S. We got to go into libhal storage. So those will make sure they go into the appropriate places. So that's pretty much what we're doing when it comes to deprecating these packages. Now next up, we have shifting the libhal-soft responsibilities. So libhal-soft is responsible for doing these three items. The one on the bottom is the one that we're going to remove, which is contain generic implementations of libraries. So RC servo was moved to libhal actuator, and SD card was added to libhal storage. Will be added to libhal storage when it's ready. Now, I wanted to kind of describe the other things that libhal-soft does so people have an idea of what to expect from it. I believe some of the writing might not be consistent with what's written here, but I do have a plan to update the documentation to reflect this. But libhal-soft responsibility is to contain wrappers for libhal. So for example, things that you pass a libhal resource or libhal interface into it, and it basically implements the same interface, but it does something extra for you. For example, we can have thread-safe wrappers for I2C, SPI, and other things like that. You may think to yourself, actually, this is a bit of an option here, but what's the purpose of this? Why not maybe just write the drivers in such a way that they're thread-safe? And the answer to that is that if we wanted to do that, we would need to it would make the driver itself more complicated and make it have to manage a lot more stuff, which means that using the driver in times when you don't need all of that ends up being, you end up paying for what you're not really going to use. And that's where the wrappers come in. They allow you to extend the possibilities and the power of that particular driver. And if we use templates properly with this, we can also ensure that we can get devirtualization so that you don't actually lose any performance cost. It would be the same vtable calls that you'd expect normally. So that's the thing. I'm sorry, you'd only have one level of vtable calls. You wouldn't have the 2 layers where the thread safe version would then call the internal version as one virtual call to get into the thread safe version, and that thread safe then calls the deeper implementation. That's 2 virtual calls. We can eliminate that using virtual. So not virtual. We can eliminate that using template arguments and putting the full type there. Now, another thing that we can also do is wrap things such as like we have an inverter. So what you do is you give an input pin to a inverter, and what you get back out is something that basically inverts the logic. So if let's say there's a class that's like a button class, and it defines the button being pressed as 0 and defines it being the button being pressed as being like 1, and then or like how should I put this? I guess the thing to say is that let's say you have some sort of a button class where it expects some voltage to be, let's say, low to indicate that it's on and high to indicate that it's off, something like that. And rather than needing to make that class handle like a Boolean to know, oh, what's the polarity of the thing I'm reading. If you have a pin that already fits that polarity, you just give it to the driver, it's done. If you need to invert it, you could just pass it into the inverter, pass that into the class, and it would just be done. And you'd also be able to do the same trick to ensure that you don't have double virtual calls. You can flatten it. So that's what the wrappers are for. They are there to kind of take a thing and modify it slightly for some use case. And then the other thing is converters. So these are things that take other interfaces and make other interfaces out of them. For example, the easiest ones are bitbang, I2C, SPI, and whatever else you like. So bitbang means to take 2 output pins and have software emulate I2C or SPI or whatever interface you need to do. The utility of these is that if you're working with a chip that doesn't support one of these things, like let's say it doesn't have I2C, it has like an SPI bus and a UART port, but that's about it, maybe a couple GPIO. Well, if you wanted to talk to sensors and you had the pins and you had the resources, you could just take 2 output pins and go. It may not be it's not going to be the most power efficient, but if you don't care about that, if you're in an industrial setting where you have power is not a problem and you're only drawing like a couple like milliwatts, then yeah, it doesn't matter. If you just want to keep the cost down, that's what you're looking for. Yeah, so that's the kind of the idea. Is bitbang allows you to get resources from areas where you normally would not be able to get those things. Same thing with SPI. And then possibly in the future, we'll have one for UART. We could potentially have one for CAN. I don't think it'll ever, actually, I'm certain it will never happen that we'll ever have one for USB. I think that's silly. I think we can have converters for quite a few things. And also, converters can also like do, I hope, more than just simply bitbang stuff. For example, I've always imagined a way to create a UART port using SPI, where you utilize, or specifically, you utilize like 16-bit SPI, such that like when you send a single clocked out byte, you would be able to, you basically you'd only control 10 bits. The other bits would just be filled up with ones to create space for each individual byte you send over the TX line. And you could basically implement this with a version of SPI that allows for like multiple bytes, or you could just use DMA SPI or whatever SPI you have that allows for very close clock cycles and all that. Sorry, I'm rambling on a little bit, but basically that's the idea of libhal-soft. It contains wrappers and it contains converters for things, and we can potentially make a lot of really cool converters for things, and I'm kind of excited to see what clever ideas we come up with in the future. All right, so let's look at STM32 generic SPI. This is, I've done this pattern before. I don't think this is anything really strange. I bet the STM HAL is written the same way. I wouldn't know. I don't even know if it's open source to that degree, but I use it. I've seen it. I don't really use the APIs that much. Now, here's the thing. The question I asked on the Discord was, do you see a difference between these two pictures? I mean, there's table 117 and table 130. The chapters are different numbers, and yet it seems that everything looks almost identical. Yeah, there's some spacing. This thing says reserved here, and this thing just chops off those extra numbers. But that's the cool thing, is that like the offsets are all the same, the bit patterns are all the same. Everything about this thing is pretty samey. And the cool thing about it is that they are the same. STM likes to copy and paste their peripherals between their chips, because why not? If you already have all the internal mechanisms, why would you reinvent the wheel? Actually, it's kind of upsetting when people reinvent the wheel when they don't need to reinvent the wheel. If it worked the first time, just re-implement the thing in the next thing. So then when they make a new STM device, they just say, oh, do we need some spies in there? All right, cool, just copy and paste a couple of these and connect them. There's a third document that I went to confirm that this was a pattern, and that was enough to convince me that we should make our own generic STM versus trying to make two separate ones for all these different devices. I actually even continued looking up other ones, and I think I got up to like 5 devices that I looked into where I was looking at their SPI and their CAN to see if they're any different from each other, and the answer is no, which is great. It means that we can, by the time, if we implement most things that STM supports, we will have covered the entire HAL that STM's HAL does. Maybe there's some things that, no, actually, yeah, we would. If we can do all the drivers that are in one of the STM's data sheets, we get most of them for everywhere else. The only things that we wouldn't get are the new things. Like I was looking up a STM chip that supports MIPI CSI. That is a protocol that is used for cameras. And I forget which CSI and DSI. I think DSI is for display and CSI is for camera serial interface. So I don't know what the real differences between those two are, like the lower level, but that's the thing. But it has it, so that's cool. Next up, let me show you a little bit of what the code looks like. So looking at this driver here, something might look a little strange compared to other libhal classes. One thing you may notice here is that there is no public HAL SPI here. It's not inheriting SPI. It is not an implementation of the SPI interface. It doesn't need to be. I don't want it to be. Here we have a configure function. It all kind of fits the same look, but there's something a little different about it. It has another parameter called peripheral clock speed. And then transfer is actually identical to HAL SPI, so nothing's different there. But now we also have like this use void pointer. I may change this to a standard. I'm probably going to change this to a standard uint pointer, just so we don't have to do reinterpret cast stuff. It means that we can do more things in const expr versus having to leave const expr to go into what would be runtime land by using reinterpret cast. Now, reinterpret cast, just as a little side note, doesn't have any runtime costs. But there's a potential that by having more of your values be more const expr in context, that the compiler can do a little bit of wizardry for you. But I digress. So that's the differences here. You may be wondering, why in the world do we have this p peripheral clock speed? And actually, I think I'm going to show you in the example after I go through the next bit here, which is looking at these two separate SPI classes. They're different namespaces. One's STM32F411 and the other one's STM32F1. Now the constructors are different. We're going to consolidate these. Like I want a runtime version of this over here, and I want a bus param version of this over here. The bus param version here with the auto here is a concept, and this allows us to, I said this back before, it's part of the initializers, but you can pass in like a thing that's like HAL : bus chevrons 1, and then the compiler will be able to tell you if you use the wrong number. This way, if you use some sort of stuff to configure this at like a higher level with like some const expr like configuration file, or if you want that extra check, like you only want to choose the right thing, you never want to choose anything outside of it, and you don't need to have it do things at runtime, you can use this, and then it'll, if you're outside the boundary, it can tell you. So yeah, that's the only little difference here. Runtime just allows you to choose the thing at runtime, if that's applicable. Now in here, these two actually do inherit HAL SPI. So these are implementations of HAL SPI. And the only thing we have in here is the peripheral and peripheral ID and the generic SPI, and then we'd have that driver here. So with that, I'm going to kind of show you what the insides look like, because I think they're really cool. And I want to, whenever we build a driver for something, to have it in our mind to check around to see if other STM devices or other devices share this. And also a reason why I didn't want to use STM's ST-Link software to implement all this stuff is because now they may not like this. This might be maybe this is like maybe it's a bad move to say this publicly, but in their license, they say that you cannot use these drivers for anything outside of their products. And I would like to use some of the Chinese implementations of the STM boards to see how those work, especially some of the ones that use a RISC-V as an alternative to ARM. And we can continue to use the same exact driver code between the two, but with their requirement, that would that would prevent us from going there. And as far as I know, they just reverse engineered it. So having our code not be able to work on that device that just so happens to choose a really good implementation of how to do SPI, to me seems like a no-brainer to just skip that. So another little reinforcement of why we write the drivers we do is not just for funsies, it's not just for it's not purely just for experience, and not even always for control. It's also just a licensing and legal thing. Let's take a little bit of a look. So, hold on a sec. All right. So, let's do this. Let's go and take a little look at, I had an idea in my head. Yes. Let's first start off by looking at an implementation that uses SPI. And actually, this is just the header. We already showed you that. So let's go to the source. And I think this is the thing that I think is really cool about this, where if we go over to SPI here, you can see how much source code is here. There's only around about 122 lines of code. And if you look at the constructor, what we do is we get a number. From that number, we have this little switch case, like we have this function called bus number to peripheral. There's a little switch case for us. This probably could also be way more optimal. Like I probably don't have to do all this stuff, but I wasn't trying to be the smartest. I was just trying to make a thing that works and I thought was easy to debug. And maybe sometime in the future I will change this up to something that's a little more efficient. But here we have a way to change the bus number into a peripheral and then into a peripheral ID, and then we use that peripheral ID as a switch to figure out what our registers are. Yeah, we probably can combine them into a single struct and then return it, sure. But yeah, so we have a couple calls to make that happen. We also have a call to MSPI driver using the unsafe token and then passing in the peripheral address. Note that this driver is not meant to be used by like just normal code. The reason why it's in a header is just because other drivers depend on its layout in order to create their own layout, meaning that they're members of other classes. So in order to make sure those other classes can use them, it's beneficial to put them in the header. I could have done an array of a certain size and gone from there, but I do feel that is more cryptic and difficult to understand for not much gain, I don't think. I just don't think so. And also I'd have to manage the destructor for it wouldn't be trivial. I think, actually, I don't know if the destructor, oh no, never mind, I take that back. The destructor for this one's not even trivial either, so that wouldn't matter actually. We wouldn't lose out on a non-trivial destructor. But the thing that I was kind of looking for was not having to do memory management, because you have to construct it in here, and then I just need to make sure that I delete it here. Not the hardest thing, but now every person who wants to use your SPI, every implementation of SPI for all the different chips that we're building up, we'll have to make sure we do that. Otherwise, we'll have issues. So here, all we're really doing, the only thing that the SPI for a particular board has to do is just figure out what peripheral we're using and then configure the pins for it and then leave. And if we have additional types of pins, that'll be additional constructor parameters that can be passed in order to tell it how exactly you want to set up the pins. And actually, I think at some point, we might also want to have a version of this. I need to add a constructor that basically skips the pin configuration so that the user can configure them themselves if they have a way that we just don't support yet. So they have a way out from this, because the alternative they would have to do is potentially configure these back to where they were before after it's called the object, which is kind of annoying and error prone in my opinion, because if you mess that up, if this thing changes, it can be, well, actually this shouldn't change, but yeah, I think that's a bit much. So we configure all the pins for the appropriate thing with the appropriate like push pull and all that. We map them correctly. If we're not in here, we throw an exception, we power on the peripheral, and then we execute the driver configuration. The driver configuration, all it does is call the SPI driver's configuration, and then we pass in the frequency of our peripheral. The reason why we held a peripheral ID and we kept it and we constructed it from the bus number was because we need it to turn on and off. Well, one thing is turn on the device and also be able to turn off the device, but to also be able to because each STM has a different clock tree, meaning that the way that the signals from a crystal to an oscillator to all the peripherals is different for each one of them. Knowing what the frequency for anything is unknowable unless you know the exact platform you're on. So each one of these platforms has their own frequency functions to tell you what those things are. And because that's not generic, there's no way to do it for all STMs. This is something that's why it's a second parameter. The peripheral understands how to get that information for itself, and then it can pass it into this configure. The configuration for this sets the clock rates and the scalars, the prescalars, all correct so that we get close to the value that we need, and that's all we need to do here. And that's why I didn't make it into I didn't make it into an implementation. Also, if I did make it into an implementation, then this couldn't be inlined, or it's unlikely it would because I didn't put it into the header. But if the linker was sufficiently smart and was able to notice, hey, I can replace this call with the contents of this call because it's not a virtual call by any means, then we could get that advantage. So there's a benefit to removing virtual when we don't want to. If I can choose if I can get this to happen, I would love it if there's only one layer of virtual that happens with any driver. The multiple layers of virtual can become a performance hit. So moving over to transfer, all it does is call transfer with the appropriate inputs. P data out, P data in, and P filler. And the rest is handled by the generic driver. And I want you to also notice that there's no difference between this and the driver that's in here. Click on this one. The only thing that's really different here is that we have more SPIs. The address locations are different. Actually, they might even be the same too, actually, except for these other ones. Ooh, crazy. The way that we do the clock control, the configuration here is a little bit more complex. So there's that. And then power on and configure like we did before. And then this just is the same thing. Although we hard coded this in for now because we don't have a clock tree available yet. And then transfer the same thing. So now making a driver for SPI becomes simply getting the clock tree, getting the power, getting the pins configured. After that, you now have all the pieces you need to make a SPI driver for your particular platform. And that's the pattern that I wanted to show. Just simply having this thing that generically does it for all these other things, and all we really are doing here is making that shaped to our interfaces, and then also utilizing constructors in order to allow the user control over how this thing's going to operate and what pins are getting configured and that kind of thing. And yeah, so I think that's pretty much it for the meeting this week. Please join us in the next 2 weeks for our next meeting.